Today's lesson is theoretical probability, but because we've been looking at the iBook and your notes haven't been quite as consistent as they have been the rest of the year, I wanted to throw up all the vocab words that we've seen so far. So the first is generic probability, or the chance that an event will happen. And remember, to calculate probability, you take the number of outcomes for that event, whatever event it is that you're looking at, and you divide it by the total number of possible outcomes. Experimental probability, you use the same formula, but you take a look at what actually happened when an event was performed. Theoretical probability, same formula, but you take a look at what should happen when you perform an event. And then finally we've got our sample space, and that is when you list all of the possible outcomes for an event or series of events, and it can be used for theoretical probability. The sample space is not typically for experimental probability. All right, so we've got two learning targets today, or two essential questions. How do you calculate theoretical probability, which I think most of you are fairly familiar with, and how does it compare to experimental probability? Now, we looked at that a little bit when we did some activities in class, but I don't know if we really nailed down what I wanted us to, so I want to go over that in the video as well and make that explicit. All right, so we've got a bunch of marbles in a bag. What's the probability that if we randomly grab one marble out, it is white? So first, determine the number of outcomes in that event. Well, there are 9 white marbles. Then we determine the total number of outcomes. In this case, how many marbles are in the bag? 8 plus 2 is 10, 6 plus 9 is 15, and 10 plus 15 is 25. So we set up our fraction, and we simplify if possible. In this case, 9 and 25 don't have any common factors, so that's our probability. Typically, leave your probability as a fraction unless I specifically ask for it in another form. All right, example B, probability that we pull out a primary color. For those that maybe aren't familiar with primary colors, those are red, yellow, and blue. So we've got 8 plus 2 is 10, plus 6 is 16. That's the number of favorable events. Those are all of the marbles that are primary colors. And again, our total number of primary colors is 25. Can't simplify this probability either. Last example on this page, what's the probability it is not red or blue? What I meant by that, because now that I'm looking at it, it might be a little bit confusing, that it is not red and it is not blue. So the marbles that are left are the yellow and the white ones, so that gives us 11 marbles out of our 25 marble total. Now we're going to compare experimental and theoretical, and I'm going to talk about what typically happens with experimental probability when you perform an event a lot of times. So our first event, Lucy rolled a die 50 times and recorded her results. So to compare the theoretical to the experimental, we need that percentage. When you look at the theoretical and the experimental as a fraction, unless they have the same denominator, it's very hard to compare your fractions. So we're going to go ahead and calculate the percentages. I'm going to start with my theoretical. And then we'll calculate the experimental and take a look at those two. Now, theoretically, when you roll a die, what should happen is you should get one out of every 6 rolls. So I'm going to take that fraction, divide it, get a decimal, and then turn that into a percent by multiplying by 100. That is the same probability whether you're rolling a 1, a 2, a 3, a 4, a 5, or a 6. And I don't quite have enough room for all of those. And I'm just going to write the percentages for the rest of them because that's the number we're going to use to compare to our experimental. All right, for the experimental, we can set up that fraction again the same way we did on the first page. So for rolling a 1, she rolled the die 50 times. So to roll a 1, she actually rolled a 1 5 times. So 5 out of 50 gives us our fraction. Dividing that, we get a decimal of 0.1, turning that into a percent, multiplying by 100, or moving that decimal 2 places to the right, we get 10%. I repeated the same thing for all of them. 4 divided by 50 times 100 gave us 8%. For rolling a 3, 10 divided by 50 times 100 is 20%. Rolling a 4, 8 divided by 50 times 100 gave me 16%. For rolling a 5, 12 divided by 50 times 100 gave me 24%. And for rolling a 6, I did 11 divided by 50 times 100, and that gave me 22%. So, comparing our percents, when we take a look at these, the one that most closely matches the theoretical was the 4. 16.6% for theoretical, with 16% for experimental, was almost exactly. The rest of them are off by quite a bit. I'm going to hold off on a true comparison until we get to the next one, and I want to talk about what happens with rolling 50 times versus 500 times. All right, so we're going to follow the same process. We already know all of our theoretical probabilities are 16.6%, so we're going to keep that in the back of our mind for each number on the die. So now I'm going to create a chart for the experimental, just like I did on the last page, for rolling a 1, 2, 3, 4, 5, and 6. So what I did on this one is the same process to calculate the percentage of rolling a 1. You take 82 divided by 500, that's the total number of times you rolled the die, and then you multiply by 100 to get your percentage. So this would be 16.4%. And I'm just going to go through and jot these down quickly. For 2, I got 16.6%. For rolling a 3, I got 16.8%. For rolling a 4, we got 16.4%. For rolling a 5, it was 16.8%. And finally, for rolling a 6, I got 17%. So, taking a look at these percentages compared to the theoretical, they're almost exactly the same. They're all within, I think the one that's off by the most is 0.4%, which is very minimal. So what I want you to understand, looking at this one, how far off some of those were, 8%, that's half the theoretical percentage. So we rolled a 2 half as often as we would expect to roll a 2 when we roll the die. But the more times you perform an experiment, the closer your probability gets to the theoretical. If we rolled the die 1,000 times, the percentages would be either identical or within 1 to 0.2% away from the theoretical. It's called the law of large numbers. You don't need to memorize that, but what I want you to understand is the more often an event is performed, the more closely the experimental percentage will match the theoretical percentage. And here are your U-Try questions. The first one has to do with a deck of cards. In my experience, not all students know what's in a deck of cards, so I wrote that out for you. Don't forget there's 2 red suits, and then the clubs and spades are both black. And then we have what are called face cards, the Jack, Queen, and King, because they have faces on them. So use that information to answer the probability for the first 3, and then we've got some comparing experimental to theoretical on the last one.